So my name is Marie. I'm from Maynooth University in Ireland, and this is joint work with Matt Luckock and Rosemary Monaghan. So I'm going to just briefly touch on a few different topics today, but I'll focus on formalizing requirements in such a way that they're actually verifiable, because I know we're all dealing with quite a few requirements. So I suppose I should introduce what I mean by verification, because sometimes the word can have many meanings. What I mean is that we're trying to determine whether or not a system meets its requirements. And there are many approaches, as we've seen throughout the Values project. There are formal approaches and less formal approaches, but these include things like testing, simulation-based testing, formal methods, runtime verification. There are many others. For example, even field tests would amount to some kind of verification for a system. I suppose the main take-home message about software verification is that it is necessary for certification in critical domains and to demonstrate that standards are met. For example, some particular standards may even recommend the use of a particular verification technique, like formal methods, for particularly critical systems. So what do I mean when I use the word formal verification? Well, formal verification isn't just checking, it's proving or disproving the correctness of a system with respect to a certain formal specification or property. And that's why it's important to formalize the requirements, which I'll move to in a little while. But I'll stick on this for a second. So just wanted to say that there are two broad categories of formal method. Again, there are others, but basically these things consist of model checkers, which exhaustively examine the state space. And there was a really good talk last time about model checking, so I won't repeat too much of that. The other category of formal method is a theorem prover. So a theorem prover usually provides a deductive proof of correctness for the system that the formal specification or property is preserved. And these techniques are particularly useful, as I mentioned, when a high degree of reliability is sought for the system, or to provide robust evidence for use by regulators, again, to demonstrate that the system obeys a particular standard. So I'll just recap model checking without repeating too much about what was said the last time, because it was a really great talk. Model checking exhaustively explores the state space of a model to check whether a logical property is preserved. So when I say the space of a model, usually you have a model of the system that is written maybe as a state machine or something like that. Then against that state machine or model, properties are written in some sort of a logic, and for model checking, it's normally a kind of a temporal logic. And then the model checker checks automatically whether or not the property is preserved for every part of the state space in the model that was constructed. And if the property is violated, then the model checker will typically produce some counterexample to say why it couldn't show it for every single trace. The main, I suppose, limitation of model checking, although it's very useful, is that it does suffer from the state space explosion problem. So as the model gets larger, then it becomes more difficult to check every state. It takes up more computational power, and it is a limitation, although this is a very useful method. Again, more information. There was a great talk the last time, so I've linked that here. So theorem proving is a little bit different. So in theorem proving, you provide a deductive proof of correctness. Again, that a model, so you construct some model of your system, obeys a particular property. And as I said, properties are usually written in a logic. There are many logics, but for example, you can consider a property in first order logic. Theorem provers are automatic and sometimes interactive, which requires user input to discharge the proof. Interactive proofs, although they're very useful because the user can drive the prover, they can be very time consuming. And theorem proving is often quite a long process, or it can be. However, it does not suffer from the state space explosion problem that the model checkers suffer from. So yeah, just a brief overview of the two main verification techniques. So they're formal methods, and formal methods can be applied at different points in the development cycle, including but not limited to requirements formalization, specification and design, source code analysis, runtime verification, to name basic but a few. There are many other different points in the development cycle. The message here is that they can be applied throughout. Of course, as I mentioned earlier, and as a few people have alluded to, verification is or can be a costly and time-consuming process, and that's whether you're using formal methods or not. However, you can mediate this by using good design practices, and I've just suggested a few things that are useful there. So things like detailed requirement formalization and elicitation can help to identify holes in the requirements at the beginning of the project. Of course, designing a system to be modular is I suppose best practice, but it makes the verification task easier because you can isolate specific components of the system. Of course, you should always isolate critical components so that you don't have to wade through, for example, a learning component to find the bit that's making a decision. And in my experience on different projects, usually a heterogeneous or corroborative approach to verification using multiple techniques, and multiple techniques I mean both formal methods, different kinds of formal methods, but both formal methods as well as less formal approaches like testing or simulation-based testing really are the best way to ensure that you have verified to a high degree. And this sort of heterogeneous approach allows you to simplify the verification burden by verifying specific parts of the system in tools or techniques that are most suitable. The only issue is that you have to also ensure the consistency between the models, and that can be difficult, but I will touch on that again briefly at the end of, well, near the end of the talk. So I'll begin by getting onto values. So in values, we're working on use case 5 with the industrial partner. So I'm going to just, I suppose, summarize some of our work on this project so far. So what is use case 5? Well, use case 5 is this wonderful aircraft engine controller. It's called a FADEC, which is something I only learned about in January, so forgive me if I'm saying it wrong. It stands for Full Authority Digital Engine Control, and the objective of this engine controller is to monitor and control the engine, such things, components such as fuel flow. In fact, I think its main objective is to optimize fuel flow. Of course, there are other things it does too. It responds to pilot input, and there's quite a lot of sensors involved that it gets input from. So when we were tasked with verifying this system, we asked for requirements. We were given some requirements from our industrial partner. And so here is just a sample of one requirement that we have been given for this use case. It says that under sensor faults, while tracking pilot commands, control objectives shall be satisfied. And then it gives an example of some of these control objectives are. And basically that specific variables are within specific limits. Now, although this requirement is useful, it tells us something about the system. It is not very easy to verify in the form that it currently is in. Because, for example, it doesn't describe what it means for a sensor fault to occur. Of course, an engineer will know what that means. But when it comes to verifying the system, we need to write these properties down in a way that's traceable, and that we can, rather than letting someone use their intuition when they're given this requirement, that it can be properly documented. It also doesn't tell us things like what are the values for settling time or the overshoot. And it's not even clear if those within the brackets, if that is a complete list of the controlled objectives. And of course, coming from, I suppose, I hadn't much experience with this sort of a system before this project. It's not even clear what tracking pilot commands means in this context. Now, of course, as I say, the person developing this will know what these things mean, but these things should be made explicit in the requirements so they're traceable from the beginning until the end. So, yes. So what were we going to do about it? Well, we started using FRET. It is a formal requirements elicitation tool. It's developed at NASA Ames in California, and it supports the formalization, understanding, and analysis of requirements. It provides a user-friendly interface, which I'll show in a second, with diagrammatic explanations of the semantics for requirements. Users use a restricted subset of natural language that they call Fretish, and it embodies a temporal logic semantics. Again, I'll show examples of that in a second. But the key thing here with FRET requirements, they fit this template shown on the slide. So they might have a scope, which allows you to write down that the requirement is only relevant for particular scopes of system behavior. Then you can specify conditions, which are, the point after which the requirement must hold. You then assign this to a component, so you can say which component has to obey this requirement. Then use the shall keyword to say that this shall happen, and you can specify timing to define the point at which the response should occur, and the response is usually that some property is satisfied. So FRET is open source and available online. So what does it look like, I guess? So here's a screenshot of the adding a requirement interface in FRET. So you can see over here, I'm not sure if you can see my mouse. So here we give every requirement a requirement ID. It can have a parent requirement, and I'll talk about that again in a minute. It is assigned to a project. In this case, we've assigned it to the project called Engine Controller. And we've written what you can add, which is really useful. You can add these rationale and comments. So you can add the natural language text for the requirement, and you can even add comments about this to help you understand that when you go back. So then we formalize this requirement, and it looks a bit like this. So if sensor false and tracking pilot commands are true, then the controller shall satisfy control objectives. So you can see it's still quite vague, and I'll discuss that again in a second. But just to mention before I move on, that FRET also provides this diagrammatic semantics. So it gives us this diagram, and it also provides the user with, I didn't actually expand this here, but it provides the user with the meaning of each of the constructs in the diagram. So the TC stands for the triggering condition. So in this case, the triggering condition is that sensor false and tracking pilot commands is true. And when that is true, then the response is control objective, so it should hold. Basically, at the beginning of time, anything can happen, then this triggering condition is true, and at that point, the requirement must hold, and that's what the orange is for. Okay, so moving to the next. So again, looking at this a little bit closer, we can see that the requirement in FRET or in FRETish is, well, it's more concise, first of all, than the natural language requirement. But the act of formalizing it in FRET allowed us to, although we kind of knew there were some things that weren't well defined beforehand, it explicitly identifies which bits that need more detail. So for example, we've used Booleans here for sensor false, tracking pilot commands, and control objectives. So it's obvious to someone reading this requirement in FRETish that those things haven't yet been expanded, and that obviously they should be for more detailed requirements, depending on, of course, the level of detail you want to go into. So if we expand this a little bit, so basically what happened after that was we got a hold of some sample test cases from our industry partner, and they're just, I copied them into the rationale section here, so that the sensor value deviates at most plus or minus or from the nominal value, and or the sensor value is not available, which is what it means for there to be sensor false. So in order to decompose this, the original requirement, we considered these test cases, and that, as you can see, allowed us to make the requirement far more detailed than it was here. And this FRET gives us this parent-child relationship between requirements, which allows us to group things that are related to one another together, so that you get this sort of, I suppose, traceability again between the parent and child requirements. Now I did mention this briefly, but I didn't show an example earlier. So formalizations down here, FRET has a LTL semantics, so it produces future time and past time LTL. And if you click on those, this is what it gives you. So although they don't look very nice here, and I'm not going to go and explain what every single symbol means in them, the LTL is useful for translating to different tools. So if you wanted to use a model checker, for example, FRET can export these LTL semantics depending on which kind you want. So yeah, as I mentioned, I've showed, okay, I decomposed one requirement. We did far more than that. But anyway, beforehand, sorry, I'm ahead of myself now. So the sensor value, yes, we added in more detail to this requirement, and we do have a lot more information than we had previously. So you can see it's more verifiable, I guess, because we know exactly what we need to look for. Although we still have some unknowns, so you could refine this requirement further. We still don't know what the value is for settling time min, for example, or we don't know what OR is. But these can be added later. So yeah, as I said, a requirement can have many children, and we have constructed quite a few others from the original requirement. For example, here we have one that considers the overshoot control objectives being met. So it's similar. I think in total we have about 19 requirements currently, but we are working on making them more detailed, more concrete, so that they're more useful for the formal tools that we want to use. So you know, it's great. We have some FRET, we have some LTL, but FRET does also support a connection with other tools. In fact, you can connect a Simulink model to FRET, so you have to parse it first into a language that FRET understands, and then FRET will generate CocoSim contracts that are used to model check with Kind2. And in this way, the way that this works is you import your Simulink model into FRET, and you map the parts of the requirements which have been pulled out. So for things like the variables, the values, and the components of those of the requirements, you can map those to their counterpart in the Simulink model, and for these contracts to be generated. So you can see here we didn't add it in, but you can add in which part of the model you import the component, and you add in the type, the data type. So it provides this automatic translation into CocoSim contracts that we verify against the model using the Kind2 model checker. So, of course, LTL semantics, as I mentioned earlier, can also be used to generate, can be used with other tools, but to generate runtime monitors for the implemented system. And we actually did that in a prior project. We used the FRET requirements to generate runtime monitors for a robotic arm, and the runtime monitors were incorporated into the robot operating system implementation in Python for the system. So it was full traceability kind of from requirements to implementation monitors. You can also use the FRET requirements without the timing constraints. And if you notice in the previous requirements, we didn't actually use the timing constraints that are available in FRET. And in the requirements that we got from our industrial partner, most of them didn't require any sort of timing constraints. And that makes it easy to specify the requirements in other formalisms. For example, if you wanted to use a theorem prover or another specification language like Event B, it uses first order logic, the requirements without timing constraints can be very easily translated into them. Okay, so next I just want to briefly discuss some of the work that I was involved in prior to the values project. And I must emphasize that the aim of these slides is to demonstrate how the sort of requirements formalization that we have done fits into a larger system verification methodology. And so if you consider a methodology, this is a sample that we published at NASA Formal Methods this year. So trying to design your system for formal verification, you can consider these steps. These are by no means a complete list of steps, but you begin by characterizing the initial system, which could be simply writing down what it's supposed to do, or talking about what the objectives of the system are. You would develop an initial system model, perhaps in something like Simulink. Then you may perform some hazard analysis, like what Sylvia mentioned earlier with the FMEA hazard analysis. After the hazard analysis is completed, usually you will find some problems, and you will define mitigations against those hazards. And from those, you will develop safety requirements. Once those mitigations and safety requirements have been identified, usually what happens is you go back, refine the system model according to the mitigations, And then you kind of loop back to step 2 and you perform more hazard analysis until you reach a point where you've got an acceptable level of risk in the system. So at that stage, once you have these safety requirements, all your mitigations are in place. Your safety requirements are, I say, formalize is the wrong word, because at this stage they will be natural language requirements. So once you have those safety requirements, then what you can do is formalize your requirements using something like FRET and create formal models of the system. And then, of course, the formal specifications for the requirements. So after that, then you might perform verification and simulation potentially at system and component levels to ensure that you've covered everything. And then you would document your results if you needed to build a safety case, for example. And for this particular work, we were using a case study of an autonomous rover. But this methodology, as you see, is quite broad, and we think that it could be useful to explore this further during values. And it does incorporate, as I said, it does incorporate some of the approaches touched on today already, as well as at the previous training session. So again, I'll mention this is from prior work, but this follows the methodology on the previous slide. And we instantiated that methodology with specific tools. In the top half, you can see the tools are in red. So the advocate tool in the top half is for assurance case development. We don't intend to do any assurance case development as part of our work at Maynooth, or currently don't intend to do any assurance cases development as part of our work at Maynooth on values. However, for that prior project, we did. So we followed through the steps. We characterized the system. We did some hazard analysis. We figured out what the mitigations and requirements were. We updated the system model, and then we made models in numerous different modeling formalisms. We had a Simulink model, a Lustre model, and an EventB model of the system. But the main part that's relevant for the values project is this sort of, we then formalize the requirements in FRET, and we use those verification tools to verify them. So I'll just now zoom in on the bits that are most relevant for values, because I didn't want to start off with part of a picture. It didn't make sense. So basically, we've currently started to formalize the requirements in FRET. As I said, we currently have about 19, 20 so far. But of course, we are continuing to refine them and continuing to add more detail. Once we have formalized these requirements, we intend to translate them into CocoSim and Lustre. So Lustre is an intermediate language for CocoSim, which uses the Kind2 model checker. And that'll be based on the Simulink model that has been input by our industry partner. And later on, I've left the EventB stuff in here as well, because everything has limitations, and CocoSim may not be able to, of course we have to investigate this, but it may not be able to adequately specify or verify all of the properties for the project, so we may also need another tool. And I've just included EventB here as an example, so then we would also have EventB requirements, and we could do proof with Atelier B for that. And I did mention this sort of system level and component level analysis as well. So we would use a tool so CocoSim is interesting because it allows you to do compositional verification. So if we can verify all of the components and that they match their individual requirements, then it allows us to derive the system level properties and verify them from the component level properties. So yeah, I think that's all I wanted to say for that bit. To conclude then, basically, I suppose the take-home messages from this talk are that formalized requirements are useful for verification and traceability between the verification artifacts. Our use of FRET so far in this project revealed ambiguities in the natural language requirements that we can make more explicit later, and we can talk to our industry partners about that. So FRET can act as a useful bridge for communication between the academic and industry partners, and that's something that we completely agree with. Although we all talk about verification and validation and requirements, it's often the case that people have different mental models of what these things actually are. So by using a tool like FRET, it makes these differences more explicit, and it does help with communicating between different people from different backgrounds. And of course, formal requirements can simplify formal verification tasks because they look more like a logical property than a natural language requirement does, and they can help streamline the development process in that sense. Okay, so that's all for me. But before I take questions, I would just like to advertise that as myself and Matt Luckett are running the third workshop in formal methods for autonomous systems. I believe this call for papers was already sent out to the values mailing list, but just in case you haven't heard of it. We're hoping it will be hybrid with some in-person attendance in Maynooth, although it will be online in all cases anyway. So yeah, the deadlines are the 30th of July. So yeah, please get your papers ready. Other than that, I'm happy to take questions on the requirements as well. Thanks.